Welcome back to ECE 501B. As way of announcement, if it's easier for you to turn in the project on Monday to give me a physical write-up, you can turn it in class on that Monday, the day after it was originally scheduled to be turned in. But if it's convenient for you to put it in the Dropbox, you can do that on Sunday or Monday. I've extended it a day because somebody said, I want to turn in a hard copy, which is fine, and it wasn't easy to turn in a hard copy on Sunday since the building is locked up on Sunday. It's even locked up for the mailbox drop on Saturday, so any weekend completion doesn't work if you're trying to submit a hard copy. As a reminder, the teacher course evaluations are due on the 11th, which I guess that's the last day of our lectures in this class if the 9th is the Monday. Our last time to lecture will be a week from today. Today is the 4th. So we only have 3 more lectures and we have to get through all of the next textbook in 3 lectures. And I don't see too many helmets, but maybe you need to bring body armor and helmets. We might go really quick through this material. We won't get through the entire textbook, but we'll start to begin that process is the idea, so that you can get comfortable with the definitions, the connection with linear algebra that or finite dimensional vector spaces that we've developed this semester. And a lot of times it's the old adage, if you're somebody that's an expert with a hammer, you solve all of your problems with a hammer. If you're building something, you always have that tool. Well, now I'm hoping that your tool is finite dimensional vector spaces, and you can now start to, when you see something new, you go, oh, that's similar to the eigenvalue eigenvector problem, or that's just a generalization of this idea of what we were doing in finite dimensions with orthogonal basis vectors. And that's what we'll get into with the functional analysis. The final exam is, oh yeah, it was 2 weeks from Monday. We're on Wednesday, aren't we? So that's a little less than 2 weeks away, the final exam, and it's at 6 p.m. on Monday the 16th. Today what I would like to do is finish up chapter 10. I think we will do that because I'm simply going to sort of define trace and determinant out of all of chapter 10. Then we will look at a couple other ideas relative to finite dimensional vector spaces, a pseudo inverse, and if you've been looking at some of the reading material, Penrose is the name of that author that's written this big book, but now you've just seen 4 chapters of that in the reading material. But this is the Penrose for that particular text. This is him that's invented this pseudo inverse, and it's an application of SVD, singular value decomposition. That's one way to find a pseudo inverse. And then we'll look at principal component analysis, which is really looking at finding eigenvalues and eigenvectors and isolating on the largest, or the eigenvector associated with the largest eigenvalue. That's principal component analysis in a couple of sentences. Then we will move into Frank's, the second textbook, functional analysis, which is not finite dimensional vector spaces. Now it's infinite dimensional vector spaces, or a signal space or function space, and we'll try to motivate that with Fourier analysis. And we'll show that this transfer function is like an eigenvalue. Meaning if you understand eigenvalues, now you have this transfer function that's a function of omega, and you have an infinite number of omegas in this frequency domain, and that transfer function now is representative of or analogous to these things we've been calling eigenvalues. And our eigenvectors will become eigenfunctions, and an eigenfunction will be this e to the j omega t. this spinning phasor, so to speak, with omega determining how fast or the frequency that you're spinning that eigenfunction. So now we'll have eigenvalues and eigenfunctions to replace what we've been talking about, which were eigenvalues and eigenvectors. So let's finish up the textbook by talking about trace and determinant, two ideas that we will develop mainly with respect to matrices. But we will deal with those right now in terms of operators. So the trace and determinant of an operator can be found based on what we've already talked about previously, and in particular the characteristic polynomial. So let's see where that comes from. Suppose that we have a vector space V. If V is a complex vector space, and we have an operator T that belongs or is operating on that complex vector space, then the characteristic polynomial of that linear operator T is, I think last time we defined it to be this polynomial Q of Z, which we could write as a product of factors that all involve the distinct eigenvalues of that linear operator T. And so we might have this factor Z minus lambda sub 1, and maybe it has multiplicity D sub 1. D sub 1 could be 1. If lambda 1 was repeated twice, D sub 1 would be 2. And we can just keep doing that. Up to, let's say that we have m distinct eigenvalues. Once we have that characteristic polynomial, we can evaluate that by replacing Z with the linear operator T, or the matrix representation of T, but I'm going to get loose with my notation and just say Q of T. Is that okay? T is in general a linear operator. I'll just sort of equate that with its matrix representation. This characteristic polynomial of T can now, if we replace Z with T, can be all pushed together and find that we have now this polynomial in this matrix that is a polynomial of powers of T, and the highest power of T is little n, where n is the dimension of our vector space, capital V. Well, if you multiply all of those lambdas and z's out, you will find that the next coefficient, including multiplicity, so if lambda 1 was repeated twice, we would have lambda 1 plus lambda 1 plus lambda 2 plus lambda 2 plus lambda 2 if lambda 2 was repeated or had multiplicity 3. But I'm just going to write them as lambda 1, lambda 2 up to lambda sub n. That now is the coefficient preceding the n minus 1 power of T. And you can just keep going down in powers of T, and eventually you will get to the constant, which is now minus 1 raised to the nth power, where n again is the dimension of V, times this product of eigenvalues. This product of eigenvalues is actually just the determinant of T, and this sum of eigenvalues is what's called the trace of T. And those two items, trace and determinant, fall out of or appear in this characteristic polynomial expression for Q of t. So now I might abbreviate that trace to be TR of t. And from what I've just shown you, I'm saying that that's this sum of all of my eigenvalues. And that sum includes multiplicities. Now, if we're just given the matrix representation of T, is there an easier way to find the trace without having to compute the eigenvalues? Because sometimes that's a little ornery to compute the eigenvalues of a matrix. If we have a matrix representation of T, then the trace of T is actually just the sum from, let's say, I equal 1 to n of the diagonal entries in that matrix representation of the linear operator T. Or if I just sort of list those two ideas as matrix facts, trace and determinant, then if I'm trying to compute the trace, if I have a generic matrix A, the trace of A is simply the sum of the diagonal elements in that matrix A. And I could say that's the sum from I equal 1 to n of A sub I. And I could compute that pretty easily as a number, but then I know that that's related to all of my eigenvalues since it's the sum of my eigenvalues, n eigenvalues. Yes? So now it doesn't matter what base, so the question was, is the matrix upper triangular? And the answer is it does not have to be. It doesn't matter what the basis is for the representation of the matrix. And I'm not going to show you that. Axler actually goes through a long list of trying to convince you that it does its basis independent. Whatever the matrix representation for the linear operator T is, you can now sum those diagonal entries, and they will be equal to the sum of the eigenvalues of that matrix, irrespective of the basis that you're representing that matrix in terms of. The determinant might be written many different ways. You might just see it as these vertical bars surrounding the matrix A. I might write it as the determinant of A, but again, this is just the product from 1 to n of eigenvalues lambda sub L. Those are matrix facts, and that's really what I'm hoping you remember, but there's a few things that we can also take away or connect with what we've already seen, or to help us during the, let's say, the analysis or processing of some of these ideas. For T, an element of this linear vector space V, the determinant of T, which we might write as determinant of T, is related to the constant term in that characteristic polynomial. Is the constant term, which we've already shown in the formula is the constant term in the characteristic polynomial times minus 1 to the dimension of v. So the constant term in the characteristic polynomial times minus 1 to the dimension of v is going to be then related to your determinant of t. That's really all that's saying. And if we're dealing with complex vector spaces, then we know that this determinant of t is just the product of eigenvalues. Again, this product includes multiplicities. If you have eigenvalues repeated, you would need to repeat those in the product. So it might have lambda 1 times lambda 1 times lambda 1 if lambda 1 had multiplicity 3, for example. Here's a proposition. We don't want to give up on all of those that we've been used to seeing. An operator is invertible if and only if the determinant of t is not equal to 0. So now if somebody says, oh, can you invert that operator, and they happen to slip you all the eigenvalues, and one of those eigenvalues is 0, you can instantly say, I'm sorry, but that operator is not invertible, because the determinant is 0. And that determinant, if you remember from your linear algebra, an inverse of a matrix, you're dividing by the determinant of that matrix, and if it's 0, that doesn't make any sense. That's no good if you're trying to divide by 0. And the proof is really related to the notion that I just said. Remember, an operator is non-invertible. Whoops. If and only if it has a 0 for an eigenvalue. And in both fields, in both the complex and real vector space cases, the determinant of t involves this product of eigenvalues. So the determinant of t is equal to 0 if and only if there exists a lambda equal to 0. It only takes one. It doesn't take 2 or 3 lambdas equal to 0. It just takes the one. So if you want an operator to be invertible, you need to make sure that its determinant is non-zero, doesn't equal 0, which means you need to keep away from having eigenvalues that are 0 for that operator. Another sort of result that we can use to our benefit if we're trying to do some computation or find the characteristic polynomial if we don't want to do it one way. Note that for t, a linear operator on this vector space V, and lambda and z being in the field of numbers, real or complex, that we decide, lambda is an eigenvalue. I'm getting sloppy here, I guess, with my writing. Is that okay? Lambda is an eigenvalue, an e-value of t, if and only if, that's what the double-headed arrow means, if and only if z minus lambda is an eigenvalue of zi minus t. So now we're saying we actually know that the eigenvalues of zi minus t are z minus lambda if we know lambda is an eigenvalue of the linear operator t. And the reason that is, this isn't really a proof necessarily, but it really sort of is. Here's a justification, because if we look at rewriting that, if I said, oh, here's a true formula. If lambda is an eigenvalue of t and v is its corresponding eigenvector, then zv minus tv I could write as ziv minus tv. I could just insert an identity matrix between this scalar z and this vector v without a problem. I can now factor out the vector v, but if I look at this upstairs, this is now ziv minus lambda v, isn't it? And so now if I bring that one down, I have z, and if I get rid of this I now have z minus lambda times v. But this should look like an eigenvalue-eigenvector equation again. Here is a matrix, and here is its eigenvalue, and v is the eigenvector. So this is true if v is an eigenvector of t. Is that okay? So now zi minus t has an eigenvalue of z minus lambda, if lambda is an eigenvalue of t. That now allows us, or provides us with a way to compute the characteristic polynomial. This result lets us compute the characteristic polynomial via the following theorem. The theorem being, if t is a linear operator on v, then the characteristic polynomial of t equals the determinant of zi minus t. So if you want the characteristic polynomial of this matrix T without having to compute the eigenvalues of T, which is the way we would have produced the characteristic polynomial up until this point, now you can take the identity operator, put z's on the diagonal of that operator, subtract this is now the matrix representation of the linear operator T, from that and compute the determinant of that. And that will now give us the characteristic polynomial of z. And this is what you've used probably in your linear algebra classes anyway, is the determinant of zi minus t is the characteristic polynomial. This is true based on that previous result that we just gave. If I looked at the determinant of A, we defined that to be the product over I of the eigenvalues of A. So these are we know that result. Well, that then implies that if we're looking at the determinant of zi minus t, we know what the eigenvalues of zi minus t are from that earlier result, and we can find this to be just the product of those eigenvalues. But if we do that, this is now z minus lambda 1, z minus lambda 2, z minus lambda sub n, but we know what that is. We've called that the characteristic polynomial, and that's then our proof. So this is the characteristic polynomial, and that's now another way of computing the characteristic polynomial of a matrix that might correspond to a linear operator T. We can simply compute the determinant of zi minus t. So if T is three-dimensional, that won't be too difficult to find the determinant of that zi minus t. And if you have a calculator that does symbolic algebra, TI-89, the TI-Inspire, maybe the HP-50, it can perform that symbolic math for you and produce the characteristic polynomial. Questions on that? Yes? So the question, I think, is I'm confusing my terminology, maybe, that you want to change this to a t. So now in terms of my abusive notation, I was saying A might be the matrix representation of T, but now I'm using T as the matrix representation of T itself in this last line. So to be consistent, maybe I should just do it in the previous formula and say the determinant of T, this linear operator, is the product of its own eigenvalues. And then in the step before, or in earlier work, we said, oh, if lambda is an eigenvalue of T, then z minus lambda is an eigenvalue of zi minus t. And we can use the same formula. Is that sort of what you would make you feel better about that discussion? If that's the case, we'll leave it like that. Okay, so now I'm not juggling A's and T's, B's, M's, whatever. Okay? Hopefully then you're feeling really good because that completes Axler. That's now chapter 10, and let's look at a couple more concepts dealing with finite dimensional vector spaces before we move into the infinite dimensional spaces, or the signal spaces, or the function spaces, which is the functional analysis text by Franks. So before we do that, let's look at a couple of things. First, let's look at this issue or idea of a pseudo inverse, which goes by many, many different names, but we'll just call it the Moore-Penrose pseudo inverse. And we'll try to sort of motivate why this might be needed, or why you might need to do a pseudo inverse instead of a full-blown or an actual inverse. First, let's suppose you have a map. And this map actually might represent a measurement system. And we'll say that, suppose you have a map, well, let's say that this could be a measurement system, meaning we may know that we're measuring some quantity, but we can't measure that quantity directly. We can only measure it through this linear relationship. Suppose you have a map, T, that's mapping between two vector spaces, U and V. So again, if you allow me to abuse my notation, suppose that I allow that linear map T to also be its matrix. So now M is equal to TW, with W living in U. Let's say that's a finite dimensional vector space of dimension capital N, and M is in the output or codomain V, which is a finite dimensional vector space, let's just say of dimension N. We now have M as our output vector. We wish to use the output vector M to infer something about W. Really, we would like to be able to determine W by measuring M, is the idea. And we just know this relationship exists. We maybe can't measure W directly, but we can measure M, and we know this relationship between M and W through this linear map T. So we know T, we know M, we don't know W. Is that okay? And we're trying to find W. So we wish to use the output vector M to infer something about the input vector W. And in particular, we might be asking the following question. What is the best linear method? It's linear because we have this linear map T. What is the best linear method for estimating W from M? And we may call that estimate W hat. What's the best way to estimate W given M, knowing T? How do we sort of estimate W from that relationship? So now here is answer 1. So now we're going to have a bunch of questions and answers. Answer 1. Suppose U and V are the same. The input vector space is the same as the output vector space. And suppose this linear map T that's living on both, so I could say is a linear vector space of U or V, is full rank. Have I defined rank? I think sort of in talking I have. But that means this map has full column rank or linearly independent columns, or it has linearly independent rows. All the columns are linearly independent, all the rows are linearly independent. It has full rank. So if U is the same as V and T is living as an operator on that space and it's full rank, then the best estimate of W, which we've called W hat, the best estimate is actually exact. And that estimate, W hat, is just the inverse of T. So if you're given M, you can now hit that on the left with T inverse, and that will give you your estimate of W. But we know that M, we know its relationship to W. That's TW. But if T is full rank, it has an inverse. T inverse T is the identity. So W hat is equal to W. Is that okay? This was just the relationship between M and W. M was equal to TW. And if T is full rank, then we can find its inverse, and we'll just operate on that measured output vector M with T inverse. That's answer 1. And that assumes that this linear map was full rank. Now, what if we don't have that? Answer 2. Suppose we are still have equal or the same input and output vector spaces. Suppose U and V are still equal, but T, which is this linear map, is no longer full rank, is not full rank. Meaning if this, pictorially, if this was U, not YOU, the letter U for this vector space, and this is now the output space V, then if it's not full rank, then we could have little pockets of vectors in V that point to the same point in V. And what does, we've called that something. So this is now many vectors in U map to the same vector in V. Do you remember what we called that earlier this semester? Now we have a non-trivial null space, don't we, essentially? So this is not an injective map, it's non-injective. So we could say T is an operator that is many to 1 non-injective, and we had a theorem, didn't we, earlier, maybe even in chapter 3, that had these 3 equivalences. It has an inverse if it's injective or surjective. Since it's non-injective, we no longer have an inverse. So we don't have an exact way of finding W now. So this is telling us that we have no inverse of that linear map T, if T is not full rank. Well, that just opens up some more questions. Question. Let me say question prime. In this particular scenario, we could have a lot of W hats sort of sitting over here that give us particular m's, the same m. So which W hat do we pick? If we have 6 of those to give us 1 m, which of those 6 W hats do we pick? Maybe we pick the smallest one. And how do we measure size? With norms. So maybe we pick the W hat with the smallest norm. Whoops, I'm answering my question before I even ask it. So here's the question. Which of many possible W hats should we pick? That's pretty rhetorical now, isn't it? You know the answer. I just gave you the answer. So let me write down the answer to question prime. We pick the one that has the smallest norm. Now, we could also deal with other scenarios where we do not have an exact or where an inverse does not exist. Let's look at those before we start trying to find the expression that gives us the minimum norm solution. The same thing happens in terms of many to one. The same thing happens if M, was that the dimension of our output space? If capital M is much less or is less than N, then we have a non-trivial null space also. In the previous discussion, we had M equal to N, but T was not full rank. Now we're saying, let's just consider different possibilities for M and N. First, what if M is less than N? So M is 3 and N is 10. Now you have a lot of columns and not very many rows. You have 3 measurements to try to estimate 10 variables. You had 3, the dimension of capital M is 3, capital N, the W's, you have 10 coordinates in that W. So now you have this matrix that's 3 by 10. And I hope now you go, whoa, I probably have some combinations of that I could map into the 0 vector. I now have a non-trivial null space. So this case, same thing happens when M is less than N, also produces a many to one scenario. And in fact, this one is non-invertible. And in fact, it's under determined. We maybe only have 3 numbers trying to give us information on 10. So we have under an undetermined or an underdetermined system. Again, even in this case, we seek to find the minimum norm solution. All right, we're almost finished with all the possibilities. M is equal to N with T not full rank. M is less than N, says we don't have a exact or we have a non-invertible system. The only one we haven't looked at is if n is less than m, if m is bigger than n. If m is bigger than n, then the system is overdetermined. Now maybe we have 20 measurements to try to estimate 10 values. So if m is bigger than n, then the system is overdetermined. So a unique solution should exist but the matrix representation of T is not square. Now we have a 20 by 10 matrix. How do we invert that? Well, fortunately, all of those different scenarios can be solved using the same expression, the pseudo inverse. That's what we're trying to show. So all of these solutions, or all these situations, can be addressed by finding what we'll call a reconstruction operator we can call P, that minimizes some error, and we'll define that error now. That minimizes the error, and we'll define that error E to actually be the square of the norm of this difference, TW hat minus M. We want to try to find a W hat which, when operated on T, minimizes the norm, the distance between TW hat and the measured values that we collected M, where M might be overdetermined, or the expression might be overdetermined, it may be underdetermined, or T may be non-full rank if W hat and M were the same dimension. Well, if you go through the process of this expression or this error, you can see that that's just this inner product, isn't it? It's the inner product of TW hat minus M with itself. And you can apply the linearity property between the expressions in the multiple slots. And you can put all of those together, and then you can take the derivative of that error with respect to W hat. You're trying to minimize this expression with respect to the choice of W hat. If you do that, you will find that the partial of E with respect to W hat ends up being the following vector. It's 2 T dagger. Ooh, that's a big dagger, isn't it? The adjoint of T times T W hat minus M. I'm not going to derive that, but you can go home and look at maybe a second or third order example and push that through and see that if you take the partial derivative of that expression, which, what do we know about the norm in terms of its final type? Is it a vector? Is it a matrix? It's a scalar, isn't it? So now we're just differentiating a scalar. We'll be differentiating something that looks like, you know, a W1 times some values. And so we can differentiate that with respect to W hat. W hat has different coordinates, and that will stack up with respect to each coordinate. So we'll have the partial of E with respect to W hat 1. That'll be the first coordinate. Partial of E with respect to W hat 2. That's the second coordinate. Now we have a vector, and it has this structural form. What have we learned about minimization problems in other classes if we want to minimize something? We do what with the derivative? Set it equal to 0. So if we set this guy equal to 0, we can now find the minimum. We're trying to find the W hat that minimizes that error. So this is equal to 0 at the minimum. Well, that 2 is just a scaling. It's a number. I can divide both sides by 2. That goes away. And this now leaves me with T dagger T W hat minus T dagger M equals 0. Or if I put the one term, if I add T dagger M to both sides, I now have T dagger T W hat equal to T dagger M. But we know something about T dagger T. That's square. So if it has an inverse, then we're good to go. Let's just assume that it does for now. If we can invert T dagger T, then we can operate on that from both sides, and we now have a formula for W hat. And this resulting expression is our pseudo inverse. This is that, what we called the reconstruction operator P. P is now equal to T dagger T inverse T dagger. And that's the Moore-Penrose pseudo inverse. All right, let's play devil's advocate. I just assume the inverse exists. T dagger T. What if it doesn't? First, we know that it's always square, but let me write down, I'm answering my questions before I ask them, aren't I? So first, note 1. If T dagger T not invertible, it's always square. So that's not the issue. It may just be that it loses rank. If it does lose rank, then there's actually sort of a numerical fix to this. And I'm not going to, but it can be shown. We can show that this reconstruction operator P is equal to the limit as epsilon approaches 0 of T dagger T plus epsilon I inverse times T dagger. And as long as epsilon is bigger than 0, we have an identity matrix at least, and that then allows us to invert that parenthetical formula. So this always exists on the right-hand side. And it minimizes the error. So if T dagger T doesn't have an inverse, we can add a identity operator to that with a small scaling amount, epsilon, and we can sort of make that epsilon as big or as little as we want. As the smaller it gets, the closer it's going to get to the true reconstruction operator. All right. Yes. So the epsilon makes that invertible. Yes. The question was this little modification to T dagger T, if it's not invertible, now we're adding in this diagonal matrix that has epsilons on the diagonal. And that makes that's if we just erased this T dagger T and I said, okay, epsilon I, what kind of an operator is that? And did we talk about positive operators or not? We did, didn't we? That's now a positive operator. The eigenvalues are all epsilons, aren't they? They're all positive. It has an inverse. And so really what you're doing is you're sort of allowing for zero eigenvalues in T dagger T to be pushed into the positive range so that this quantity can now be inverted. That's the idea. Now, if you don't like that, you can compute this pseudo inverse another way. So again, we're in notes, but P can be easily, let me say, obtained from the singular value decomposition. And now I'm really abusing notation because U and V were my vector spaces before. Now they're going to be matrices in this second note, meaning T, let's say that's now a matrix, we can write that as U sigma V. I'll just say US V transpose. Then the reconstruction operator P, I don't know why I'm switching all my notation, P is now effectively the inverse of T. And if we inverse something, remember U and V were consisting of orthonormal columns, so their inverses are simply transposes. And when you inverse something, these matrices switch around in terms of their order so that this is now V. We can't assume that S has all non-zero singular values. There may be some zero singular values, so we can't just invert all the entries in S, which is a diagonal matrix. So I'm going to call that S tilde. But this one we can transpose U transpose. Meaning S in this is made up of the singular values along the diagonal that I'm calling S sub I, and S tilde is going to be also a diagonal matrix, but it will be made up of two possibilities. It'll be the inverse of S sub I if S sub I is not equal to 0, but we'll force it to 0 when S sub I is 0. We're not going to be dividing by 0. And that makes for a nice reconstruction operator if T is not square, if T loses rank. If T loses rank, some of these S sub I's will be 0. Well, that's okay. We'll just set those particular diagonal terms to 0 in the pseudo inverse or in the reconstruction operator. And we can compute U and V transpose from any matrix T. That's our second note. So if you have the SVD, you can find a pseudo inverse. And that's equal to the Moore-Penrose pseudo inverse. And that's pretty easy to compute. You just have to invert the singular values along the diagonal, and if some are 0, you just set those diagonal entries to 0. The third note before we get into the next topic is if T in fact is invertible, then we get back that the reconstruction operator is just T inverse. P, by definition, is T dagger T inverse T dagger. But if we invert that term in parentheses, we now have T inverse T dagger inverse times T dagger. But T dagger inverse times T dagger is the identity matrix. And we said that T inverse existed, and so now P, the reconstruction operator, is just T inverse, if we use that formula. So now we have this P reconstruction that works in all the different cases. Non-full rank, M less than N, M bigger than N. So this works in all cases. And that's now this pseudo inverse. If you're trying to solve a problem, and maybe it's a measurement problem, and you have fewer measurements than you have variables, you could use an SVD on that matrix and do a pseudo inverse and find a good approximation to that W, calling it W hat, and all the other cases. That's the pseudo inverse. Let's now see if we can talk about one more topic, which is called the principal component analysis. And I think one of the papers, the reading papers, is on this. And some of you might be doing your report on that. Suppose we are given some x's in some set S, or we're given a set of those vectors x. Given x in S, a set of vectors in a finite dimensional vector space V, where the dimension of V is some capital N. So now we have this big set of vectors that we're calling capital S that are in this finite dimensional vector space V, and the vector space V is of dimension N. We want to know what is the shortest list, or how many vectors can we get away with to basically represent a vector in this whole set, capital S. What is the shortest list that can represent a vector in S? And typically, in a lot of my classes, I'll say it depends. That's the default answer, right? And what this one, it depends on what S is, what this set represents. Meaning, as far as some examples, suppose we have V is R2 and S is also R2, meaning we have this two-dimensional vector space x1 and x2, and now somebody says, how do you represent a generic vector x? Whoops. An arbitrary vector in R2, how big of a list of vectors do we need to represent that arbitrary vector x? We need 2, don't we? So an arbitrary vector in R2, we need a list equal to the dimension of V, which is 2. What about, so that was example 1. What about example 2? Suppose again V is R2 and S is the x1 axis. Now we have our x right there. How big of a list do we now need to represent capital S? We really only need one vector, don't we? So now our list is of dimension 1. Let's say A, which is now this A, 0. And if I had a line and I lived on that line, I would still just need one vector on that line. It would be of a list of size 1. But what if somebody sort of gives us some messy numbers in this two-dimensional plane R2? Meaning now we have x1 and x2, but now maybe somebody says, oh, the head of your vector x is represented by one of those dots. So V is equal to R2, and S, let's say, is clustered maybe it looks sort of like it's clustered around x1 is equal to x2. Well, the idea is, can we actually find the principal component in this collection of vectors so that now maybe we just need a list of length 1 in that principal component direction? That's the idea. There's maybe no perfect vector making this list. No perfect short list, but what if we were interested in the best short list of some size? And obviously this is more interesting if we get into much bigger dimensions than a two-dimensional plane and scattered points in that two-dimensional plane. This is more interesting in higher dimensions. So now what we want to do is address the following question. In what basis do we obtain the best, let's say, k-dimensional approximation to x for all k that are less than or equal to capital N, where N is now maybe our collection of vectors. The answer is the principal component basis, and sometimes you might hear this referred to as the Karhunen-Loew expansion, or the Karhunen-Loew basis, also called, and hopefully I can spell this to where you can look it up, Karhunen-Loewe. So you could look up principal component analysis, Karhunen-Loew expansion, etc., and you'll get the information, hopefully, that describes this process. Let's see if we can sort of quickly talk our way through some of this. What we want to do, based on what we've already done in this class, is it would be nice to find an orthonormal basis B that now minimizes the expected value of the norm of x minus its approximation x hat. Meaning if we have an orthonormal basis B, then we could theoretically express x in terms of that basis by what? Finding the inner product or its weight in each of the basis vectors. So we have xb1 times b1 plus xb2 inner product scaling b2 all the way down to wherever we stop. Let's say it's n-dimensional. We now have xb sub n weighting the direction b sub n. Well, to create our estimate, x hat, then what would we do? Well, we would pick x with b1 and b1 plus x b sub 2 weighting b sub 2 down to whatever dimension we'd finally decided to stop at, let's say p weighting b sub p, where we're assuming that this little p is less than n. So let's just consider the very first case. Let's consider p is equal to 1. So if p was equal to 1, if we were trying to estimate this multidimensional set of data with just one vector, then we're saying x hat would be x b1 b1. It'd just be the first component and in that direction of b1. Or that's also saying that we're saying that we now have x minus x hat squared. What does that equal? Well, now x hat is going to take away from x this very first piece, or the very first vector, weighted by xb1. And now we want to find the size of these last n minus 1 terms that form x. But we know what that means in terms of the norm squared, because we've assumed these b's are orthonormal. If these are orthonormal, we know that we have this squared all the way down to the other inner product, x to the b sub 1 squared, meaning the expected value of this norm squared is equal to the expected value of this sum from I equal 2 to n of the inner product of x with b sub I squared. That's from what we've already talked about. And what does that really say? In order to minimize this x minus x hat, which just consists of the last tail n minus 1 terms, then if we can maximize the x inner product with b1, that's the same as minimizing this expected value of x minus x hat, because that will make this tail smaller. Is that making sense? So if this is now the same as, so minimizing the expected value of the norm of x minus x hat squared is equivalent to maximizing the expected value of the inner product of x with b1. And what you will find is that you would build this up, and maybe I'll complete this after class in just notes, but you're essentially looking for the largest eigenvalue, and b1 is the eigenvector associated with that largest eigenvalue associated with, let's say, a collection of vectors x. And we'll stack all of those up into rows into something big we'll call capital X, and we'll be looking at an X transpose X, which we can then find the eigenvalues of, or we could find the singular values of X and pick the largest direction in the associated with the largest singular value, or we'll look at the direction, the eigenvector associated with the largest eigenvalue in this collection of vectors little x that make up capital X. I'll try to fill that in after class since we're out of time, but that's the principal component analysis. You're really looking at eigenvectors and trying to pick out the biggest eigenvalues and their respective eigenvectors. So next week we'll get into Franks.